So this is EE 619, lecture 4. So far we have seen the unified current model for both the NMOS as well as the PMOS transistors. We saw some of the short channel effects, and I want to clarify a few things about the velocity saturation current model. Do you remember the equation we derived? For an NMOS transistor, what is the current when the transistor is in velocity saturation? Mu and COX, W by L, VD sat n into VGS minus VTH minus VD sat n by 2. So this is what we had derived in class, and we saw that when we plot ID versus VDS, you will see a linear behavior till VD sat, and beyond this, according to the equation, this should have been flat, right? But just like in long channel transistors, meaning just like how you got to see channel length modulation, where the current was increasing with respect to VDS even under pinch of saturation, here also in practice you will see that once it enters velocity saturation, the current doesn't remain constant, but it will increase slightly. And to account for this factor, to account for the fact that the IDS is actually increasing slightly with respect to VDS, we will have 1 plus lambda VDS. So the unified model has already captured this. I wanted to stress on this once more. Okay. Now we'll not worry about the underlying physics associated with this. For now, just understand that even under velocity saturation, your current is going to increase slightly with respect to VDS. Okay. Now what is the slope of this curve? It will be equal to lambda. Okay. So now let's say I did this for some voltage VGS1. Now, if I plot this for another voltage VGS2, would you expect this relationship to be linear or quadratic? Why quadratic? Sorry? Square of VGS term is there. Can you show me where that term is in the equation? It will be linear, right? Under pinch of saturation, you would have expected this to jump quadratically because you had VGS minus VTH the whole square. But if it is under velocity saturation, this relationship is now going to be linear. Okay. So this is again one way in which you can identify whether your transistor is in velocity saturation or pinch of saturation. Simply change the VGS for few values and see how it is jumping, right? Okay. So now all of you know how we represent an NMOS transistor. The symbol is this, where this terminal is gate, this terminal is drain, and this terminal is source. It can also be represented like this, where this is gate, and you determine drain and source depending on which is the higher voltage. Similarly, your PMOS transistor can be represented like this. So this is your gate, source, and drain. It can also be represented like this. This is okay? Good. So now let us move on to, so before I move on to today's topic, I want to give you a question for you to think about. Let's assume that there is a transistor which is in saturation region. Let's say it is in pinch of saturation. So you have the oxide layer and you have the gate layer. Now we said that under pinch of saturation, your channel is going to get pinched off much before drain. So here is a question to think about. If your channel has already pinched off, how are the electrons from the source getting to the drain? So please think about this and see if you are able to figure out how this is happening. So the clue is, think about how the electric fields are acting in the small region. Okay. All right. So with that, we come to today's portion, which is basically to learn about the different capacitances associated with a MOS transistor. Again, as before, we will start with a MOS capacitor. So this is a two-terminal device. So technically, our analysis should be much easier to do with a two-terminal device. You have the gate node, then you have the bulk node. So let's start this discussion assuming VGB is lesser than 0. Under this condition, what is the charge on the positive? What is the charge on the gate? You'll have negative charges here. What about at the surface? You'll have positive charges. It is P-type. P-type, you have the metal, oxide, and the substrate. Okay. So now let's say I have already given VGB to be some negative value. Let's say VGB is equal to minus 0.5. Now I make a small change, delta VGB. So it's already biased at minus 0.5. Now on top of it, I make a small change. Corresponding to this, you can expect to see a small change in the charge. So let me represent this using delta QGB. Now if I do delta QGB by delta VGB for a given bias, that is for a given DC value of VGB, you see that this is a constant, correct? And what is the unit of this? Q by V. Yeah, it will be some capacitance, right? And this is how we are going to define our small signal capacitance. So the small signal capacitance, CGB, is now defined as dQg by dVg. That is, I make a small change in Vg, keeping the body constant. Then I observe what is a small change happening at the gate. Okay, small change in the charge happening at the gate. And this derivative will give you the capacitance CGB. Instead of representing it in terms of Qg by Vg, I can also represent this as dQb divided by dVg, again, assuming body to be a constant. So here again, I'm making a small change in Vg. Instead of observing the change in charge at the same terminal, I'm looking at the opposite plate. So because of that, you have a negative sign. Is this okay? So now it's possible to derive CGB rigorously by using these expressions. But of course, we are slightly lazy and we will try to get an intuitive approach for this. And we will do this by comparing all these structures with a parallel plate capacitor. So let me bring up a parallel plate capacitor. So what all factors define a parallel plate capacitor? You have two plates, right, where you have charges that are free to move. So you have a top metal plate as well as a bottom metal plate where the charges are completely free to move, right? Now, in between this, you have a region where no free charges are available. And you will have, let's say this region has a width of D. You will have electric fields that start from one plate and ending at the other plate. Now, if I make a small change, delta V, I make a small change in the potential applied to it, you would see a corresponding delta Q charge in both the terminals, in both the nodes. Is this okay? So we are going to look at all these structures and compare it to this parallel plate capacitor. Now for a parallel plate capacitor, what is the value of the capacitance? So epsilon of this dielectric into area divided by thickness. So we'll compare and then we'll see how we can apply this equation. Okay. So now let's go back to this particular MOS capacitor. Let's say this thickness is now equal to some TOX. So on top side, you have the gate, which is a metal or a polysilicon layer, which has free charges. What should form the second plate? The surface, right? The surface where now a sheet of holes are available. So these two forms the two plates of our capacitor. In between these two, we have an oxide layer where no free charges are available. And you will see electric fields that start from the positive terminal to the negative terminal. Now, if I make a small change in the supply VGP applied to this, you will see that you will have a corresponding delta Q appearing at the top and the bottom with, of course, negative sides, right? So based on this information, can you tell me how I can define a capacitance now? What should be the value of C? Epsilon naught. What is epsilon naught? Okay. Epsilon of the oxide, right? So it should be CGB should be equal to epsilon OX into, so I should give you the dimensions, right? Let's say this is the length and into the plane of the paper is the width. So it's epsilon OX into WL by TX. Now we have seen this term already. I'll call this as COX into W into L. Okay, where COX is the capacitance per unit area. What should be the unit of COX? Farad per meter square. Now, since we are going to deal with dimensions in the range of micrometers, and it turns out the capacitances we will deal with will be in the range of femtofarads, we usually represent this in terms of femtofarad per micrometers. Okay. All right. So now let us consider what happens as we keep increasing the VGB. So let's say my VGB is now greater than 0, but it is still smaller than the threshold voltage. What is the charge on the gate? Negative. VGB is greater than 0. What should be the charge on the gate? Positive. What happens under the surface? Will you see inversion charges? What will you see? You will see a depletion layer. Right? So let me call this width as some WD. Can you still identify the two plates? The top plate is still the gate, right? What should be where should be the bottom plate come? So where are the free charges now on the other side? So the body has holes, right? Now you can uncover more negative charges when the holes move to the bottom, right? So you have to imagine the other plate somewhere here. If I apply a delta Q, if I apply a delta V, you can easily imagine delta Q appearing on the gate, right? The equivalent delta Q appearing on this other side is appearing because the holes are moving away and it is uncovering negatively charged ions. Okay. So then I could write the equation of the capacitance as some epsilon into W into L divided by WD plus TOX. But then we have a problem, right? What value of epsilon would we use? So what we do is we say that this is secretly two capacitances. One capacitance between the gate and the surface. So like this. And another capacitance between the surface and the edge of the depletion region. So let me call this as C1 and C2. Then the total capacitance CGB will be equal to the series combination of C1 and C2. What is the expression? C1, C2 by C1 plus C2. What is the value for C1? Let's say C1 is the capacitance between the gate and the surface. COX into W into L. What comment can you make about C2? So what are the two plates for C2? One is the surface and the other is the edge of the depletion on this side, right? So all of this is happening in silicon. So it's some epsilon Si divided by what is the depth? WD into W into L. So as you can clearly see, C2 is a function of WD and WD is a function of the potential that you apply, right? Which means C2 can change as you change your bias. This is okay. So as WD increases, what happens to C2? Does it increase or decrease? It decreases. If you have two capacitances in series and if one of them is decreasing, what happens to the total capacitance? That also decreases, right? So let's start plotting what we have obtained so far. So here we have VGB and here I'm plotting CGB. When VGB was negative, what is the value of the capacitance? Please look at your notes and tell me. This will be equal to COX into W into L, right? What happens once VGB starts to become positive? Is the value going to increase or decrease? It is going to decrease, right? So it will keep decreasing. Now what happens after that? We will see. Now we will analyze this for the condition where VGB is much greater than VTH. So what is different now? You will have inversion charges, right? So you'll have a layer of negative charges at the boundary, at the surface. Okay, which means most of the electric fields that are going to start from the positive plates will now end with the inversion charges. Okay, and also if I make a small change delta VGB, which charge is now going to change? Is it the depletion charge or the inversion charge? It is the inversion charge, right? So now where are the two plates of your capacitance? The top metal layer and the surface, correct? So what is the capacitance? COX into W into L. Is this clear? So effectively, as you approach higher values of VGB, you will see that it comes back to COX into W into L, right? So this is the overall shape of the curve. Is this clear? Now it turns out when you are going to work with these transistors, right, in digital circuits, you are either going to use it in cutoff or in linear region, right? And in cutoff, the value is very clear. You will be somewhere here, which means the capacitance value is COX into W into L. What about in linear region? What comments can you make about the inversion layer in linear region? Is it completely established or will you be somewhere here? Linear region. Okay, so the reason why I said in digital circuits you will be using transistors in linear regions is this. In digital designs, generally the transistors are used as switches, right? And when you want to turn the switch on, you will apply the maximum available input voltage to it, which is usually VDD, right? And it is in linear region because you're using it as a switch. So if I apply Vx here, ideally I would have liked to see Vx on the other side also, right? Now, even if this is not directly possible, at least the voltage drop seen across the drain and the source would be small, right? So VDS is small, VGS would be as high as it is available to you. So it will be either in linear region or you will simply turn off the switch and make sure that the input voltage is much smaller than VTH. So you're going to work between cutoff and linear region under steady state conditions. Okay. So given that it is operating in linear region, what comments can you make about the inversion layer charge? Is it completely established or is the depletion width still increasing? Please refer to your notes from the last class. How does the channel look like in linear region? Is the channel there? Right? The channel is completely established, right? So you will be operating somewhere here, right? So in either cases, the capacitance between the gate and the bulb can be expected to be COX into W into N. Is this okay? All right. So with this, now we can move on to the capacitance in an NMOS transistor. It's roughly around VTH. Deriving it for NMOS transistor, but the same logic applies to both NMOS and PMOS transistors. So the NMOS transistor has 4 terminals, and ideally you can expect to see capacitances between any 2 terminals, right? So you'll have a capacitance between gate and the drain, which we refer to as CGD, between drain and the bulb, CDB, between gate and the source, CGS, between source and the bulb, CSB. Am I missing anything? C? CDS. Okay, anything else? CGB, right? Now about CDS, so you're basically saying that you can have a capacitance between this diffusion region to this diffusion region, right? So you have a channel in between. So this capacitance can be broken in terms of the channel capacitance. Okay, and I'll show you how it is done. Okay, so now let's start with some portion of the capacitance associated with CGS and CGD called as the overlap capacitance. Have you heard of this term before? So let's say I have N plus regions as shown here. So far, we have been drawing our oxide and gate very neatly like this, where they are completely aligned, right? In practice, by the end of the fabrication process, you would get a structure shown here, where there is an overlap between the gate and the oxide region with respect to the source and the diffusion regions. So now if I have positive charges on the gate, when I apply a positive VGS, I will easily have negative charges on the N plus diffusion regions, right? So in this small area, you will have negative charges, right? And now you can see a parallel plate capacitor forming here. Can you see? The top plate is because of this portion of the gate. The bottom plate is effectively this region where you have a lot of negative charges. Now, if I increase the delta V associated with the gate, you will see that correspondingly you will have a delta Q in the gate as well as a delta Q that gets crowded under the gate in this region. Okay. So now if this width is LOV, L overlap, right? And into the plane of the paper, let's say this width is W. Can you tell me what is the value of this overlap capacitance? So this is equal to into LOV divided by TOX. So this is equal to COX into LOV into W, right? So this is basically the overlap capacitance associated with the gate and the source. So C, gate to source overlap capacitance. Similarly, there will be an overlap capacitance associated with the gate and the drain. And this will also be given by COX, LOV into W. Now this parameter, LOV, is not under your control. It is a technology parameter. Therefore, we combine both COX into LOV and call this as some overlap capacitance, COV into W. Okay, so now in practice, the calculation is not so simple. Because of the fringing electric fields, it's not exactly COX that appears there. So when they provide a model for the COV, all of this is taken into account, right? But for theoretical understanding, you can think of this as COX into LOV. Now, what is the unit of COV? This should be farad per meter. But again, we usually represent this in femtofarad per micrometer because the dimensions we deal with are usually in micrometers. So if you get a number like this, you can easily multiply with the micrometer measurement you have, and you'll get the value of the capacitance in femtofarads. This is okay? Any confusion so far? So next we move on to what is called as the gate to channel capacitance. Given by CGC. So now we are talking about the capacitance present between the gate and this channel, right? Now, of course, we don't have a channel terminal as such in the MOSFET. So we would like to represent this capacitance also in terms of the nodes that are present in the symbol, right? So we will have to break down this gate to channel capacitance and associate with the nodes available to us, okay? So as you can see, this channel is in contact with what all terminals? It's in contact with the source, with the drain, and with the bulk. Therefore, it makes sense to say that this gate to channel capacitance given by CGC can be broken down or divided into three components. The first component associated with the source, second component associated with the drain, and a third component associated with the bulk. Okay, so now let's look at each of these components under linear region. So CGC is now 3 components. Why are they adding? Because effectively, this is a capacitance between the gate layer and something else. So one is between the gate and the source. The other we say is between the gate and the bulb. And the third component is between the gate and the drain. So CGCD plus CGCB. Okay. And it turns out this total capacitance is still equal to COX W into L. Okay. So now you know that you have a full channel developed here. And roughly when you apply a delta V on top, where are the electrons coming from? It's coming from the source and the drain regions, right? Therefore, we say that this capacitance is equally divided between CGCS and CGCD. So you have the expression COXWL by 2. This is also COXWL by 2. This is okay. And this value is 0. Now, under saturation region, so does this make sense that the bulk component, the body component of this is 0? Inversion layer is already there. In MOS capacitor, we saw that when the inversion layer is already there, the capacitance between that layer and the bulk was equal to 0, right? Because the capacitance was now between the gate as well as the channel, as well as the inversion layer, right? So same principle here as well, the CGCB goes to 0. Okay. So now under saturation region, you have a channel. Therefore, you expect this to be equal to 0. What comments can you make about this? Roughly, these are qualitative statements. Why 1/3? You remember it from the result. Okay. So there is no channel present next to the drain. Right? This is completely pinched off. So generally we say that this is equal to 0. I would be interested to know from where you got the 1/3 number. We can discuss this after the class. Okay. Now CGCS will be equal to 2/3 into WLCOX. So the total capacitance under saturation region is simply 2/3 WL into COX. So we will not get into the detailed calculation for this. So you can simply remember this result. And finally, under cutoff region, again, CGC is equal to the source component GCD plus CGCB. What comments can you make about each of these components? What should be the gate to source capacitance, the channel capacitance between the gate and the source? It should be equal to 0. Why? There is no channel. Exactly. What about this component? This will also be equal to 0. And this one? This will be equal to COX into W into L, because we are now around the lesser than VTH, right? So there is a possibility of having a depletion region. Sorry, even before that, VTH is equal to 0. So even the depletion region is not present. So you are looking at the gate and the surface concentration of the holes in the substrate. So this will come out to be COX into W into. Okay. So now let me put all of these results together. So you have the operating region. So we considered cutoff, linear, and saturation. Now you had the values for CGCS, CGCD, and CGCB. Together you have the value for CGC. And then based on this, you can now calculate the total capacitance that you will see from the gate. Under cutoff region, what is the value? What is the value? 0, 0. It's COX into W into L. So the total gate to channel capacitance is now COX into W into L. Can you tell me the total capacitance seen at the gate? COX W into L plus, so COV into W. Is this correct? Or are we missing something in this expression? We should have a twice of COV into W because there is an overlap capacitance between gate to source as well as between gate to drain. So if your VGS is equal to 0, right? So in this plot, if your VGS is around 0, then the depletion region is actually very negligible. Yeah. If VGS is coming closer to VTH, then you will see a drop in capacitance. So digital circuits, when we talk about the regions of operation, generally the gate voltage is either 0 or VDD. Okay, so let's quickly fill in this table. Actually, why don't you guys fill in this table and then I'll fill in from my end. So for linear region, what is CGCS? WLCOX by 2. CGCD, CGCB, 0. This is COX into WL. And the total capacitance becomes COX WL plus 2 times COV into W. For saturation region, you will have 2 by 3 COX WL. This is 0. This is 0. So this is 2 by 3 COX WL. And you have 2 by 3 COX WL plus twice of C overlap into W. This is okay. Now, like I said before, we are most likely going to operate either in the cutoff region or in the linear region. Therefore, I can write the capacitance, the total gate capacitance, as WLCOX plus twice of COV into W. So can you tell me what are the design parameters available in this expression? So we have W and we have L. Now it turns out for digital designs, we would like to keep our L to the minimum possible length. Okay. And the reason for this is very simple. So let's say I have an inverter like this. And let's say this inverter is driving another inverter, identical inverter. Now, if I were to make the length of this larger, what happens to the current through the transistor? Current will decrease, right? Current is proportional to 1 by L. So if I make the length larger, current decreases. And lower current means that it will take more time to charge or discharge any capacitor, which means larger delay. So from the delay perspective, we would like to have our length minimum. Now, the other part to think about this is, if I make the length of all transistors larger, the gate capacitance of this inverter is also going to increase. because the CG is proportional to length. So increasing length actually has two problems. One is it is going to increase the capacitance. Two, it is going to reduce the amount of current available for you to charge or discharge the capacitor. So I is decreasing, C is increasing. Effectively, your delays are simply going to increase. Therefore, in digital designs, L is also not the design parameter for you. So I'll bring out W, and you'll see that this becomes L into COX plus twice COV. Yeah. So the key takeaway here is that if I increase my W, the gate capacitance is going to scale linearly. Okay. So this is the key takeaway from all of this discussion. So now we have two more capacitance remaining. That is CDB and CSB. And these are called as the junction capacitance. Okay. So to start this discussion, let me first consider a PN junction. You will have a depletion region with negative ions on this side and positive ions on this side. Can you identify a capacitance here? Basically, can you identify two plates and the in-between dielectric region here? It is a depletion region, right? On this side, you have free holes. And on this side, you have free electrons. So on either side of the depletion region, you have charges that are free to move, right? And in the center, in this region, you have no charges that are free to move. And also you will have an electric field that extends from one side to the other. Okay, so you can think of this as a parallel plate capacitor. Now let me ask you this question. Let's say I have reversed bias this junction. Okay, and let's say the unit capacitance, that is capacitance per unit area at this junction is given by Cj. If I increase the reverse bias voltage, what comment can you make about Cj? Will this increase or decrease? It will decrease. Why? Okay, but is there another way to visualize this? Yeah, as you increase the reverse bias voltage, the depletion width is increasing. It's as if you have a parallel plate capacitor and moving the parallel plates away from each other. So the distance between the plates are increasing. Therefore, you can expect the capacitance to decrease. Okay. So now you will be given the unit capacitance, the capacitance per unit area or capacitance per length of the diffusion region associated with both the source and the drain. And then we have to now calculate it based on the area, right? So this area calculation is actually simple geometry. You just need to listen to the parameters. That's all. So let's start with an NMOS transistor. So you have an N plus region here and another N plus region here. You have the oxide and the gate. So as you know, there is a small reverse bias region associated with both these. Okay, and under regular operation, you would have a channel and an associated depletion region with the channel under the gate. Okay, so now let me mark all the dimensions. So first step is that we will assume that this is a clear rectangular in shape. Okay, now let's say the depth is given by xj and this is given by ls. Now as before, the dimension into the depth of this into the slide is w. So let me help you visualize this better. So I have a drain region and I have a source region. Then we have an oxide layer on top and then a gate layer on top. Is this okay? Right. So now we have to find out all the areas associated associated with this diffusion region, so this inter region, that can result in a capacitance. What comment can you make about the bottom plate? So you have to assume that the rest of the region is right. So there is the bottom plate that is in contact with the P surface. You can expect to see surface region. You can expect to see junction capacitance. Right. What about the top side? There is none. Correct. What about these three sides? There is. Right. So there is the front side, back side, and this side. Now, what comment can you make about this side? You will have part of the channel, the other part will be the diffusion region. The idea is that capacitance is associated with that region also. But in terms of for first order calculation, we can ignore this and still get reasonable value. Okay. So even in that calculation, we are going to ignore the side of the source and the drain corresponding to the channel. So first we'll write for the bottom plate capacitance. Can you tell me the area of the bottom plate? It will be LS W. Let's write that. So this is the bottom plate capacitance. C bottom. So this is Cj into Ls into W. Okay. And like we saw, there is no top plate capacitance. Now we will look at the side wall capacitances. So I'll write it as CSW. So I'll call this as CJ1 because it turns out the doping concentration seen on the sides of the drain and source region is different from that seen at the bottom. So these three sides will be slightly higher dose, called as top and plan. And it is done to make sure that the diffusion and the source and the drain regions are of the shape that we recommend. So now let us take CJ1 and we have to multiply it with 3 areas. What is the area at the front? So LS into 8 and area at the back? 3. What about this side? XJ into W. That's this will be equal to CJ1 into what is the first area? Front side? XJ into LS. Twice of this because front side and the back side. And what is the side area? XJ into W. So I can take XJ outside. So this becomes CJ1 into twice of LS plus W into XJ. And this parameter is what we call as CJSW into 2LS plus W. So my total capacitance CSB is now equal to the bottom plate capacitance plus the side wall capacitance. And this is given by Cj into Ls into W plus CjSW into 2Ls plus W. As before, W is a design parameter, so I will take it outside. So this becomes Cj into Ls plus Cj SW into 2Ls by W plus 1. This is okay. Now, if you ignore this parameter, you will see that CSB is also proportional to width, linearly proportional. As you increase your W, your CSB will also increase. Now, for general designs, it's a reasonable assumption to make that 2Ls by W is negligible compared to 1. This is okay. Now, CDB will also be equal to CSB provided both of them have the same bias. So if the Cj and Cjsw values are given, you should be able to calculate all these capacitances. Is this okay? So we'll take a break for 2 minutes. Please go through the notes and let me know if you have any questions. Just want to cover a small point. So we saw the overlap capacitance, gate to channel capacitance, etc. Now, if I want to write CGS, what should be the expression? This will be CGSO plus CGCS. Similarly, the gate to drain capacitance will be the overlap capacitance associated with the drain, as well as the gate to channel component associated with the drain. And finally, CGB is simply CGCB. And the key takeaway from all of this discussion should be, as you increase your width, your capacitance is also going to increase linearly. Okay, so we'll move on to inverters. I'll cover a small portion on inverters and then we'll continue the lecture in the next slide. So this is probably the most important module in this course, right? Because whatever we learn from inverters, we are going to apply these results into the lessons we learn on combinational circuits and finally on sequential circuits. So we are going to spend a lot of time learning about inverters so that we are very thorough with it. Okay. Now I'm sure everyone is familiar with the symbol for an inverter, right? So if I give a logic 0, what is the output? You'll get a logic 1. If I give okay, it's stuck. If I give a logic 1, the output is 0. And typically logic 1 is voltages around VDD and logic 0 will be voltages around ground. Okay, in general terms, I'll say that the typical high voltage, which we expect to be VDD, I will call it as VOH, so that we can talk in terms of VOH and VOL in terms of instead of VDD and ground, a general discussion we can have. And the typical low voltage will be VOL. Okay. And even though I said that the typical high voltage is VOH and typical low voltage is VOL, we know that in digital circuits, usually a range of voltages around VOH can still be considered as logic high. Similarly, a range of voltages around VOL will be considered as logic 0. Okay, so now let's talk about the voltage transfer characteristics of the DC characteristics of an inverter. How do we obtain this? This is also called as the DC characteristics. Given an inverter, how will you find this? So I give you an inverter. It is a black box for you. You don't know what is inside, right? You don't know what circuit has been used to build this. But if I give you an inverter like this, how do I find the voltage transfer characteristics? You apply an input voltage V in, and then you will vary this V in from the minimum value to whatever is the maximum value. Let's say it is from 0 to VDD. And you observe what is the V out for it. Okay, this is fine. So now let me give you a sample voltage transfer characteristics And then you can discuss and tell me whether it is fine. So let's say I have designed an inverter that has a VTC as shown here. So this is my V out. This is my V in. Feel free to discuss and then tell me if this VTC will work, or an inverter with this VTC can work or not work. What do you think? It will not work. Why? V in is not equal to V out, meaning? I mean, V in is an input voltage, V out is an output voltage. So what? As long as it can be identified as a logic high or logic zero, I should be fine, right? It will work. So one answer I've got is it will work. Any other comments? What do you mean by for a very less range? It will not be able to drive another inverter. Okay, so let us check that condition. So say I have two inverters. Okay, now let's assume that the voltage given to the first inverter is logic 0. So somewhere very close to 0. Let me call this as V1. And V1 is very close to 0. What will be the output? This is something slightly smaller than 1 volt, right? So what you'll see here is almost equal to 1 volt, which is somewhere here. Now for the second inverter, is this logic high or logic 0? It will fall within that undefined region, right? So for example, here I mentioned that there is a range of voltages which should be considered as logic high. There is a range of voltages which will be considered as logic 0. And there is an in-between region which is considered as undefined region, right? And we digital circuit designers are afraid of this. We don't want any voltage to lie in this region, correct? So if you have a characteristics as shown here, you will not be able to drive an identical inverter. Is this clear? Okay. So now let me give you 4 voltage transfer characteristics. And then you can tell me if there is a preferred VTC among all of us. So this time, let me assume that this is both ranges are the same. So among these 4, is there a preferred VTC? Why? It will always converge to VDD or 0. Okay, is that statement clear? Now to make that clear, let us consider the last 2. So let me call this as A. Let's call this as B. Okay, so you can do this as a homework. What you have to do is this. You take a chain of inverter, right? Let's say this is V1, V2, V3, and V4. You start with a V1, which is closer to 0, right? In a range where it can still be considered as logic 0. Let's call this as V1. Now, if you have V1 here, the output is going to be here. So this is V2. Now you bring back this V2 onto this curve again, and then find out what is the next voltage. So you have found out V2. Repeat this process and see how the voltages are appearing as you proceed through this inverter chain. Okay. Repeat the same exercise with the second VTC also. And then see if you are able to tell what is the property that we are looking for in a VTC. Okay. So we can wrap up the class here. Thank you.